Hey guys, hi, Praveen here. I welcome you to a new session on OpenCV with CloudX Lab. We are going to see basic image processing with OpenCV. We will cover translations, rotations, resizing, flippings, croppings, etc. We'll also do some basic image processing like image arithmetic, bit operations, and masking. We'll also introduce you to the concept of color spaces and the advantages of different ideas of color spaces and the different functions of color spaces which are available in OpenCV. Let's start with the first part, which is importing the necessary libraries and setting up Matplotlib so that we can plot images. I'm going to talk about a problem that we have with OpenCV is that OpenCV by default reads in data in the BGR format and not RGB. So that often ends. So when we use CV2 and Matplotlib, we usually have a problem with the way images are seen because the color spaces are different. That can be fixed very easily by basically ensuring taking the image and converting that clearly to an RGB format before outputting it. And we create a function that we can use on call in our notebook everywhere. Okay, so what I'm going to do is I'm going to show you how the image looks. We have seen the giraffe image before, and if I use a giraffe image without the remapping of the colors, it looks like this. And I'm going to show you what the image was really supposed to look like. Okay, so as you can see, the natural colors are really right. We have a natural blue, and the colors of the giraffe are also very clear and realistic. But if I don't apply the remapping, you can see the colors look very different from what it is supposed to be. It looks like it's taken in some alien landscape on, and something weird's really happened. So it's a very weird, it's a very easy way to set this up. Okay, now we're going to come to our translation. What in translation, what do we do is we just basically are able to move our entire image in a particular direction. I'm going to just show it to you by example. So at first, we're going to use a simple example of trying to move the image about 250 pixels to the right and 500 pixels to the bottom. Okay, so let's try that. Uh, so what I first need to do is I need to declare a translation matrix that specifies that clearly for me. And I'm going to apply it on my image, and I'm going to show it to you. So as you can see, I have moved the image 500 pixels to the bottom and 200 pixels and 250 pixels, about 250 pixels to the right, which is basically what I've specified here. So I'm moving the columns. So I'm moving the images along on the width side by about 250, and on the number of rows from the bottom by about 500. And you can see that very easily. I can do it. If I want to have the exact opposite, I just need to flip the directions. So if it's positive, the image gets pushed to the right side. If it's negative, the image gets pushed to the left side. Similarly, on the other axis, if I have a positive translation value, like I have here, the image gets pushed to the bottom, and if I have a negative value, the images get pushed to the top. And I'm going to see the opposite of what I've seen. So as you can see, I have it in the opposite direction. Okay, now the images can be rotated also. While rotating an image, there is a point around which you're going to pivot. So we are going to choose the center of the image as the pivot. If you want to choose an alternate point, you can choose that. But in this particular example, I am going to be using the center of the image as a point of pivot. So we're going to specify the center of the image as the midpoint of the width and the midpoint of the height. The double slash is basically the floor. So if I have a value like 13.5, the floor division will ensure that I get the value I get is 13. Okay. Now, so I'm going to execute it. And I'm now defining my rotation matrix, my translation matrix, which is a rotation matrix. It's got a center, an angle. So I'm going to first start demonstrate you a 45-degree change, and the last parameter that goes here is the resize factor. So right now I'm not doing any resizing. I'm just going to keep the resizing as 1. You can change that if that interests you, and we're going to see how it looks. So as you can see, I have the same image. Now it's rotated 45 degrees, 45 degrees to the counterclockwise side. If I want, I can do a 90 degrees or a 180 degrees. Or if I choose, I could have moved it 90 degrees to the clockwise, in the clockwise direction. Okay, so as you can see, if I have a positive value, the rotation goes towards is in the anti-clockwise direction, and if I have a negative value, the rotation is in the clockwise direction. Okay, great. Now we will talk about resizing. So okay, so what we have here, we're just going to look at, so the original image had 3993 into 2667 pixels. So this was the height and this was the width. Now, if I want to resize the image where I want the width to be 150 and and the height, I just want to make sure that the dimensions are, the aspect ratios are retained. So what I'm going to do is I'm going to say that, okay, I need 150, and the other side of the shape, I'm just going to, so the other side of dimensions, I'm basically going to scale it down by the same factor, by a factor which is 150, and the shape of the image. So this is the image I get, and as you can see, it's the same. The aspect ratios are the same, but the number of pixels have reduced. Okay. In my next example, I'm going to do something different. I'm going to scale the width or the height of the image to 150 and scale the width so that the aspect ratio is the same. If you look at it, I have done the same thing. I have I've identified the factor of the factor with which I have to multiply the width, and then I have done the multiplication and set the dimension. Okay, the other factor I think I've been spoken about is interpolation. So we have to specify what kind of interpolations we use, and we have the image here. As you can see, the size of the image is further smaller, and we can see some more pixelations now. So this is something you can do. And with CV2, I can also output the image. Now I can save this image in my directory. If I do this, so this is worked, I can even output the image. We will now look at flipping. So flipping is very easy. There's a simple function called cv2.flip. If I have, and it needs a value, if the value set is 1, it will flip along the y-axis. If the value is 0, it flips along the x-axis, and if it's -1, it flips along both the x and y-axis. Very simple. Now I'm also going to give you an example of cropping, which says if I just want to take out one particular section of the image. So I have just chose to get the section of the image that corresponds to the head of the giraffe, and I get that. It's very easy to do. I'm just going to use the image, like an NP slice property, to just get that section of the image. Okay, now before we start with image arithmetic, there is something we just need to understand, that a pixel value cannot exceed 255 and cannot be lower than 0. So both CV2 and NumPy images have a way of managing that. So NumPy basically performs what's called a wraparound. So by a wraparound, it basically means that if a value exceeds 255, the next value becomes 0. So you don't have 256, 257, 258, 259. Instead, you have 0, 1, 2, 3. Okay. And whereas what OpenCV does is OpenCV just clips, so just seals. So if you get a value more than 255, it just sticks to 255. It won't change it further. Okay, so what we're going to do is we're just going to demonstrate that. So if you just add, so if I use CV2 and if I add If I try to create an addition of 100, as you can see, right? So I've taken 200 and I've added 100 to it, and I've used numpy, a CV to add functionality. So you can see 200 plus 100 is not 300, but it's 255. It just clipped to 255. Similarly, on the lower side, CV2 will clip the values down to 0. You will never see negative values. But instead, if I use a wraparound, we have a little weirder value where it went to 255 and it just went around. So the 300 basically translates to 44, because basically it's 300 minus 256, which value comes to be 44. Similarly on the other side, if you do a negative, the wraparound happens, and whereas CV2 would wrap a number to 100, you get a number of like 206 if I use standard numpy. Okay. Now so we use CV2 everywhere, and I'm just going to show you what happens when we add numbers, just randomly add numbers to CV2. So CV2 addition basically makes an image look brighter. So it takes more of the pixel values to 255, which is white. So essentially, if you add if you increase the value of all the pixels if you just keep increasing the value of pixels, essentially because the image tends to get whiter and whiter, or it often looks brighter and brighter. Basically, just getting whiter and whiter and whiter. Similarly, if you subtract and you're taking the images closer to 0 and 0, what you get is you get a darker looking image. So as you can see right now, the image looks kind of darker. Okay, the next little thing which I want to talk about is bit operations, which are precursor to masks, which are often used a lot in image processing. So the standard bit operations are AND, OR, NOT, and X NOT. We'll see that they're exactly similar like normal bit operations, and nothing fancy. So what we'll do is we'll first create a rectangle. First, what you're going to create is a canvas that's black, and we're going to specify a rectangle, which is and I'm going to show you how it looks. So this is again a black canvas with a rectangle with the same dimensions of height and width. So it looks like a square. And what we'll do is now we'll create a circle, a different canvas, again on black, and a white circle in the middle. You've seen this before. And now we're going to demonstrate different bitwise operations with this circle and square that we have created. So if we create a bitwise AND, what we get is we get a mask that highlights all the pixels that are white in both the square image and the circle image, as you can see. So here, both the pixels, the pixels in both the corresponding images have to be white. Only then it gets highlighted, else they all become black. Similarly, but if I use an OR image, they need to be white either in the white in the square or in the circle. Either one is fine, and it works out. If I use a bitwise OR, now I'm going to use bitwise XOR. So bitwise XOR basically uses the function 1 plus 1 is equal to 0, 0 plus 1. So any one value has to be 1 or has to be white, and the second one has to be black. So it just highlights the sections where the pixel values are exactly the opposite. If the pixel values are the same, the numbers go to black. Okay, and the white is the sections where the pixel values are of the square and the circle are exactly the opposite. And the last, not the least, we're going to look at a NOT function, basically, which is just the exact opposite of the circle image which we had. So in the circle image, we had a black canvas with a white circle. And when I create a NOT, I get a white circle I get a white canvas with a black circle. Now, what mask does is, with mask, what we can do is we can take a mask and just apply it on an image which we're interested in. So what we're going to do is we're going to create a mask that would basically catch a square from any image we want. So we're going to use a giraffe image, and we are going to first create a mask. So what we did is we created a mask in the, so we have created a mask, which is basically a little square in the center of, which is exactly in the center. So if I apply this mask with a bitwise AND operator on our image, on our uh, image, as you can see, so what I have is I have exactly the center of my giraffe image taken out by a square. So this is an easy way of doing a crop or just highlighting a particular section if I'm interested in. We will use these operations more in a few times more in the latter sections of this of these videos. Okay, the next type we'll be talking about the color channels. As all of you probably know, is that any color image, it basically consists of multiple channels, a red, a green, and a blue component. Now, what we'll do is we'll access each of them separately by creating separate numpy arrays for each of them. Okay. So now I'm going to basically use a new image called a rainbow image because it's got more colors, so it's kind of looks nicer. So this is the image I'm going to use for this particular exercise. So you can see there are a few greens, a rainbow, and a person in a nice bright red shirt in the middle. Now, what I can easily split the image in its BGR channels. As you remember, CV2 basically uses the BGR format. So if I do this, I can get the BGR format. And I can plot each of these, I can just plot the red section of this image. So if I plot the red section of the images, what I'm getting is I have highlighted the red portions much highlight are highlighted as white, and the portions that don't have much red get darkened. On the other side, if I use the blue, the sections that had more blue are lighter, and the sections that had less blue are now darker. Okay, and if I take the green, the sections which had green the most are now lighter. The sections that had very little green are darker. So as you can see that the red is higher. So like, for example, this person is wearing a nice bright red shirt. It's pretty highlighted in this picture with where I'm just showing the R channel, the red channel. Similarly, in the blue channel, the brightest part is the sky, which is a nice sweet blue in a lot of sections. And a certain section of the rainbows also. And in the green component, it's mostly the grass that's highlighted. The grassy area is mostly highlighted. The rest of the part is a lot darker. Okay. Now I can actually even merge all the channels separately and recreate the image. So in case you have certain operations in which you want to work on each of the channels separately, each of the color channels, make some specific changes, make some specific filters, variations, you can do that very easily. Okay, now last we're going to talk about color spaces. So what we have right now worked with is the RGB and the BGR spaces, but there are other color spaces that are also interesting. There's something called hue, saturation, value, the LAB, LUV. Now it turns out that for certain computer vision tasks, it's better to operate in a different color space. What I have linked is I have linked a particular example related to detecting different colors robustly under different light conditions by using different color maps. So this particular link, it talks about creating a computer vision application to finally solve the Rubik's Cube. But the problem they were looking at was that the color detection, the method to detect color, was not robust enough. So you can just read we're not going to cover this particular chapter here, but essentially what CV2 does is CV2 supports a lot of different color maps, and they're very easy to use. Okay, so again, I'm going to use a rainbow image, and we're going to look at a few color maps. One color map, a very standard color map, which we use is often the BGR to gray, which is gray scaling or making an image to black and white, as you can see here. And I'm also going to show you this other ones, the HSV, the hue, saturation values, or the LAB, or the YUV. So it might, again, as I said, for certain different computer vision applications, it often helps to operate in a different color space. And with OpenCV, you can do that very easily. Thank you. That's it for this session.